In this video clip, we will see how we are going to approximate equation root by bisection method. We know the equation root is also the corresponding 0 point of a function. Previously, we know that f of x equals natural log x plus 2x minus 3 has a root. You see, this is the graph. Has a 0 point. Has a 0 point between 1 and 3. Now, how we are going to approximate this 0 point or the corresponding root of the equation? Here we got to use bisection method. What's the meaning for that? The bisection method is basically take the middle point of a sequential intervals to approximate the root of an equation until a desired accuracy is reached. For example, right here, we have a y equals natural log x plus 2x minus 3. And then we know clearly the 0 point is between 1 and 0 from the graph. How do you draw the graph? If you have a calculator, that's easier. You see, you may turn on your calculator and click on y equals. You input the graph right here. Input the equation or the expression right here. Okay. Then you may click on graph. It will show up here. This is value 1 for x. This is value 2 for x. So the root is between 1 and 2. So between 1 and 2 here. All right. So then, based on the principle here, bisection method, the principle of bisection method is we are going to use the middle point. Between 1 and 2, the middle point is 1.5. 1 plus 2 divided by 2 is 1.5. That's basically somewhere here. Okay, middle point. Yeah, we use this middle point to approximate the root. If you calculate the middle point, how to calculate? You click on second graph. Okay, you see when x equals 1, you have a value is negative 1. If you plug in value here, 1, okay, natural log 1 is 0. Okay, 2 times 1 is 2 minus 3. Final answer is negative 1. If you plug in 2, right here, this right value. So then you have a 1.6931. And then the middle point is 1.5. If you plug in, you may input one more time. You see, if you input 2 here, you hit enter, the same value. If you input 1.5, that's going to be 0.40547. Okay, this value. So it's approximately the value right here. Okay. All right. Now this 0.405 is not 0, so apparently then 1.5 cannot be the root. But we know 1.5, if you plug in here, you get a positive value, so it's somewhere here above the x-axis. Then the root must be in between 1 and 1.5. So then you choose this interval. And then what's the middle point? The middle point is 1 plus 1.5 divided by 2, which is 1.25. Okay? And you plug in 1.25, 1.25 here, you hit enter. You have a negative 0.2763. That's negative 0.277 because this 9 is greater than 5, you round it up. So you get negative 0.277 for that. Okay. Then you know 1.25 has a negative function value. So 1.25 probably is somewhere here, and then you get negative. So then between 1.25 and 1.5, the root must be in between those two values. Okay? So then you choose the average. 1.25 and the 1.5. The average is 1.375. You plug in 1.375, you hit enter. You have a 0.06845. And again you drop 4 because which is less than 5. So you got 0.068 right here. This value. Then you got positive for 1.375. Okay. So we know 1.25 was negative, you see here. And 1.375 is positive. 1.25 is on the left of this root. 1.375 is on the right. Okay, because you got positive. Now you have those two boundary points. And again, you do is you choose the average, 1.25 and 1.375. Choose the average of these 2 points, that's the middle point. So you then have 1.3125. Okay, so you plug in 1.3125. You hit enter, you have a negative value. You have a negative value. And then negative value tells us that 1.3125 is on the left. Is on the left of the root of the x-intercept. So you got to choose 1.3125 right here as a left interval. And the right interval, you know this was, when you plug in this value, you got positive. You see right here is positive. Okay, and then keep working on that. The average of these two is negative, is 1.34375, and the function value is negative. You can try that. 1.34375. You hit enter. Is negative 0.017. Okay, so this point will be the left boundary. So you put it right here. Keep the right boundary. Choose the average of those two. You have this value. Okay, so you plug in again 1.359375. You hit enter. You get 0.26. Here is 0.257. You round it up. Okay? So you keep working this way. This is the sequential interval. One is inside the other. The following one is inside this one. This interval is inside this interval. The following interval is in the interval above. You choose the average of the boundary points, plug in, then determine where you should choose this interval. This point will be the left boundary because this is negative. So negative value tells you this is left boundary. Okay. Positive value here tells you this is going to be the right boundary. You see, down the following one, you will choose this one as a right boundary. Keep the left boundary. And then keep working. You see the middle points here is quite close to the 0, approximately is 0. So you may choose this one as a root, okay, or as a 0 point of this function. So it depends on your given accuracy, okay. You did a few more steps. You see when you plug in this middle value of this interval, and this number is quite close to 0. So you may claim this is the approximation of the 0 point of this function, or the root of the corresponding equation. Here is the dynamic way. Here is the dynamic way to show you step by step. You see, you click on that, it tells you, you have 2 boundary points, and here is the middle point. So you keep working, then the middle point, then you have this point with this value 0.405 is right here. Okay, so you got to choose those two, one left, one right boundary. So then you have a left, right, and then you have another middle point. You have another middle point, you choose a value, and this value is going to be negative. So you see 1.25, this value is negative, so it's down right here. Okay, and then you got to choose these 2 points as an interval. Okay, 1.25, 1.25, 1.5. And then you choose another middle value. It is right here. Okay, so you keep working on that. You can see here we stop right here. Okay, because once you get finer scale, and it's hard to see from the graph. Okay, enjoying this animation. I'll see you next time.